All right, guys. Today we start slightly soluble salts, which is the second major topic here in chapter 17. And what we're going to be talking about or looking at is the dissolving process of a salt in water. Okay? We know when a salt dissolves up in water, what happens is that the ions separate. And you can represent this by a chemical equation. So sodium chloride solid going to sodium ions aqueous, chloride ions aqueous. I was writing this on the board. I would put water up above the arrow to indicate that I was dissolving it up in water. Okay? Now, we know that when we dissolve a salt up in water, we're breaking the ionic bond and we're separating the ions. And if we look at this process of dissolving a salt up in water and forming the solution, we know that for any solution there is a saturation point. A point in the solution where we've hit the maximum amount of solute that the solution can hold. Okay? The concentration of a salt in a saturated solution is called its solubility, or sometimes its solubility limit. For a salt like sodium chloride, the concentration of salt that is in solution at the saturation point is very high. So we talk about sodium chloride having a high solubility. Okay? But what we're going to focus on here in Chapter 17 are what are referred to as slightly soluble salts. Salts that dissolve up in water to a very, very small extent. Okay, so they're slightly soluble. This indicates that the strength of the ionic bond is pretty good in these compounds that we're going to be looking at, because think about it. In the dissolving of a salt in water, they're giving up an ionic bond for an intermolecular interaction. Okay? So slightly soluble salts do not dissolve up in water very well, to any great extent. Okay? Last semester, when we were talking about precipitation reactions, we referred to them as insoluble salts, because they just don't dissolve up well in water. We're very interested in these kind of salts, even though they don't dissolve up well, because a lot of them contain heavy metals and can be toxic. So we want to know something about how to keep them out of solution, or how much will be in solution. Okay? When a soluble salt dissolves up in water, it completely dissociates, which means the ions completely separate. We're going to assume that slightly soluble salts do the same thing. When the slightly soluble salt dissolves, the portion of it that does dissolve completely separates. So copper 2 chloride solid in the presence of water gives us copper 2 ions aqueous and 2 chloride ions aqueous. Okay? Now just a reminder, solubility of salt is the amount of solute, in this case a salt, contained in the specific volume of solution at the saturation point. Solubility is often expressed in grams per 100 milliliter, or sometimes grams per milliliter. It's done that way in geology quite a bit. Biologists might use this, especially environmental science-leaning biologists. For us though, because we're chemists, and this is a chemistry class, we talk about solubility in terms of molar solubility, which is the moles of solute per liter of solution for a saturated solution. So the molar solubility is the concentration in moles per liter of a solute at the saturation point. Okay? So the one thing I want to point out here is, notice after molar solubility I put a lowercase s. Instead of, S is going to be used to represent concentration when we're talking about slightly soluble salts. So if we place enough salt into solution to reach the solubility limit, reach the saturation point, you can think about we're at the equilibrium point for this dissolving process. If you were to put any more solid into the solution, okay, it wouldn't dissolve up. And we would see particles moving from the solid phase to the aqueous phase back to the solid phase. At the saturation point, anytime the ions try to come out of solution, they immediately go back in. Okay? Because there is an equilibrium that can be established, this process of dissolving a salt up in water can have an equilibrium expression. And we can say for that reaction of copper, well, the dissolving process of copper to chloride in water, the equilibrium constant would equal the concentration of copper 2 plus at equilibrium times the concentration of chloride ion at equilibrium squared. Okay? Now, because this is a dissolving process, we use a special designation. We call the equilibrium expressions here the KSP. SP stands for solubility product. So let's write the dissolving process for some salts, and let's write their KSP expression. Okay? So if we start with silver chloride, that's not writing real well. Let's switch over. Silver chloride solid in the presence of water goes to silver ions 1 plus aqueous, chloride ions 1 minus aqueous. The KSP here is just going to be silver ions 1 plus concentration times chloride ion 1 minus concentration. I don't include the silver chloride because it's a solid. Okay, if I had something like lead 2 chloride solid, in the presence of water, I get lead 2 plus ions aqueous and 2 chloride ions aqueous. The KSP here is the concentration of lead 2 plus times the concentration of chloride ions squared. Okay? So, give you a couple examples. Now, the value of KSP can be calculated from the molar solubility of the salt. Again, okay, the saturation point, the equilibrium point. So KSP and molar solubility are linked. So let's look at an ice chart for a slightly soluble salt, and let's look at calculating a KSP. And guys, you're going to see that these are really nice and simple. So we're going to look at page 849. Okay. Correction. Why am I looking at wrong? Sorry guys, wrong book. That's an old number. So we're going to look at chapter 17, and we are going to look at a nice problem here. Come on, book, work with me. So we're going to calculate KSP. Okay? The problem we're going to be working is 1709 on page 772. So let me change this here. well, no, let's go through this example that I pulled from another book, and then we'll do the 17.9. Okay? Here's our reaction. Calcium fluoride in the presence of water gives us calcium 2 plus 2 fluoride ions. So the KXB expression is calcium 2 plus calcium 2 plus times fluoride ion concentration squared. Now if we look at the ice chart, okay, the concentration of calcium ions initially is 0. The concentration of fluoride ions is 0. Now, for every calcium fluoride that dissolves up, I get 1 calcium, so the change in calcium, we're going to go plus S. The change in fluoride ion is going to be plus 2S. So that in equilibrium, we have S and 2S. The ice chart here is really simple. Okay? Now, if we're given that S equals 1.2 times 10 to the -4. Molar. Then what we get is that KSP is going to equal 1.2, well, I'll just do this the easy way. (1.2) times 10 to the -4 times 1.2 times 10 to the -4 squared. Let me put the square in there. And inside here, notice that we're dealing with 2S. So let me put a 2 there. So I've got S times 2S squared. Okay? So if we were to solve this, we get, let me grab my calculator, 1.2 EXP, 1.2 EXP for negative. Power times 6.9 times 10 raised to the -12 power. Okay? So, pretty good. And not too bad, right? We can handle that. Now, before we go on, I want us to remember that we can go in the opposite direction. If we got KSP, we can go to molar solubility. So what I want to point out to you here is that there's a pattern between the relationship of KSP and solubility if I have a salt dissolving up in pure water. Okay? Now let me put this note in here. Note these relationships work for a salt in pure water. And evidently I can't type today. Okay, so if we have a salt that's got one cation to one anion, the KSP is going to equal the solubility squared. If I've got two cations to one anion, it's 4s cubed. If it's one cation to two anions, it's also 4s cubed. If it's one cation to three anions, it's 27s to the fourth. If I have two cations to three cations, KSP equals 108 s to the fifth. Now you can also reverse these. If I had 3x and 1y, or if I had 3x and 2y, I'd get the same thing, just like I did up here. So we're going to look at a couple of problems. Okay? We're going to look at we can look at problem let's see. I'm going to look at problem 17.8. It's on page 771 in your textbook. And then we'll look at 17.9. Well, no, 17.8 is what I think we want to look at. Okay? Now, let's slide over here. Problem 17.8 says calculate the molar solubility for iron 2 hydroxide. So we're given the salt FeOH taken twice. Now, if I write out the reaction, I get Fe2 plus ions, aqueous, and 2 hydroxide ions, aqueous. So KSP would be iron 2 plus times hydroxide squared, or we can think about it, since this is in pure water, is S times 2S, that's squared, so that's where I get the 4S cubed. Okay, now you could cut to the chase, but I'm trying to be overly careful. Now your book gives you a chart of KSP values. For iron 2 hydroxide, KSP equals 4.87 times 10 to the minus 17. So KSP is given to 4.87 times 10 to the minus 17. So if I plug that in here, 4.87 times 10 to the minus 17 is equal to 4s cubed. Okay? So 4.87 exp 17 negative divided by 4, and then I take the cube root, I get S to be 2.3 times 10 to the minus 6. And that would be molar. It's the molarity. So, not too bad, right? You should be able to plug and chug with these. You might want to look at practice problem 17.9. It's another example of a slightly soluble salt being dissolved up in water. Okay? So you can give it a shot. Now, some general things to remember about KSP, like with all equilibrium expression. Okay? The larger the KSP, the larger the solubility is going to be. And we could compare KSPs to help us decide which salts are more soluble than others. Now, when we're making that head-to-head comparison to judge solubility of salts, we want to remember that the only time this really works is if the salts are in the same ratio. So if I were to compare silver chloride to gold 1 chloride, that would be a good comparison because they're 1-to-1 ratio. But I wouldn't want to compare the solubility of silver chloride to copper 2 chloride with just the KSPs because there's a different ratio of ions. We'd actually have to calculate the solubility to compare the solubility of copper 2 chloride to silver chloride. Okay? Now, when we think about dissolving slightly soluble salts up, sometimes we are dissolving up in a solution that contains other salts. Okay? And we can run into something called the common ion effect. Now, the common ion effect means that there's an ion already in solution that the salt you're trying to dissolve up contains. And that common ion is going to interfere with the ability of the salt that you're trying to dissolve up, dissolving up. Now let me show you. Okay? So let's say I have a sodium chloride solution and I want to dissolve silver chloride up in that solution also. Well, I want to also dissolve up silver chloride in this solution. Now, silver chloride solid in the presence of water is going to want to go to silver 1 plus and chloride 1 minus. I already have some silver ion in here. Some chloride ion in here. Let's say the concentration of this is 0.10 molar. If I did my ice chart, and by the way, you have to do an ice chart here. My silver ion content in there to begin with is 0, but my chloride ion content is now 0.10 molar. So plus S, so this is S, and 0.10 plus S. The fact that I have some chloride ions in there to begin with is going to reduce the solubility of my silver chloride, my slightly soluble salt. Okay? So let's look at an example where we're going to have to work this. So problem 17.10 in your book, it's on page 773, is going to be the example that we're going to use. Okay? In our slightly soluble salt here, it says we have calcium fluoride. So calcium fluoride solid in the presence of water is going to give me calcium 2 plus 2 fluoride ions, 1 minus. Okay? And it says we're trying to find the molar solubility S in a 0.250 molar calcium nitrate solution. So I already have calcium nitrate dissolved up in there, and I'm trying to dissolve up calcium. The KSP for calcium fluoride, your book gives you in a table. Okay, the table is on page 770. Calcium fluoride's KSP is 1.46 times 10 to the minus 10. Now, let's do our ice chart. calcium 2 plus, fluoride 1 minus. My calcium concentration initially is 0.250 because I'm dissolving up in calcium nitrate, and for every calcium nitrate there's 1 calcium, so the concentration of calcium ions in there is 0.250. No fluoride ions to begin with. So I'd be plus S here, plus 2S. So this would be 0.250 plus S, and this is 2S. Now, let's write our KSP expression. Our KSP expression is the concentration of calcium times the concentration of fluoride ions squared. Now, if I plug in 1.46 times 10 to the minus 10, it's going to be equal to 0.250 plus S times 2S squared. Now, with slightly soluble salts, and in this kind of problem, 99.9999999% of the time we make an assumption. I'm going to assume that S is going to be much, much less than 0.250. Look how small the K is. Okay, that's why I can do that. So now I get 1.46 times 10 to the minus 10 is equal to 0.250 times 2S squared. So 2 squared is 4 times 0.25 should be 1. Yep, I get 1.46 times 10 to the minus 10 is equal to 1S squared. So 1.46 exp 10 negative, take the square root of that. I get S to be 1.21 times 10 to the minus 5. Now look at S and look at our starting concentration. That was a perfectly valid assumption. And when you're doing any of these slightly soluble salt problems where you're dissolving a salt up in a solution that already contains another salt that has a common ion, you are going to make the assumption. Okay? Now, I'm going to stop right there because I've got to go do a Zoom session, and we'll pick up here next time.